Welcome back to Balvigan Bharati with Avilas Sarkar. We are doing the application part on the basics of the Bernoulli's, the base of the Bernoulli's theorem. Basically, all these applications, all the theories being built up with the basic theory of Bernoulli's. The first of its kind that we have seen, it is the Venturi meter that is applicable to get the flow rate of any flow, the in case that is a steady flow into any duct or the pipeline of a fluid, of a ideal fluid. So the next application that will learn is the is also a law of a scientist that named after him is Torricelli's law, that there will get a value. That value is the called the speed of a flux. That is some arrangement. If let's say someone reservoir is there, and from that reservoir some fluid is flowing through a small duct, so there the fluid will get some velocity of ejection. That velocity of ejection is called the speed of a flux. So let me draw that arrangement, and the topic is speed of a flux basically, and this is named after the scientist Torricelli's law. Okay, so what is the arrangement? Let me draw the arrangement. This is a reservoir full of some kind of fluid. Okay, there is some outlet, very small outlet with respect to the cross section of the reservoir, let's say. So this is ejecting some liquid out of it with a velocity v. Okay, so the cross section here is, let's say, capital A. Here cross section is A. The height of it can be assumed capital H, and the height of the tapping or the duct, the small duct, is small h, you can take. So with this the one thing that has to be assumed, as the cross section A with respect to that A is much higher, the velocity here, let's say this is velocity v1, this is velocity v2 or v, so that velocity here is much lesser than v here in point 2. This is 1, this is 2, let it be 2. So we can assume that this is approximately is 0, as because with respect to this it is much layer, we cannot even observe it to flow or come down. So the velocity of the surface of the liquid is can be taken as 0. With this assumption, if I go and use the formula for conservation of energy, as because it is a streamline flow, you can assume the conservation of energy between these 2 points, the surface, there is a point 1 and there is a point from where the liquid is flowing through that small duct. What are these? The pressure here is P0, that means P atmosphere, their pressure also P0 at this mouth. So because this is in contact with the atmosphere in everywhere, if it is contact with the air, you will get the atmospheric pressure. So pressure at point 1 is P0 atmospheric plus half rho, the unit volume we are talking, V1 square. So V1 square, what you said, this is equal to 0. This is kinetic energy, potential energy, rho g. H is the height of this. Now, as this is the the point up to which the liquid will flow. After below then there is no flow of water. So we can take this as the reference frame or reference line. This is our reference line. Okay, with this, so from there this layer height is same as h. So what is the height here? Rho g h we can take. Okay, on the other hand, the if I take the energy equation here, it is the pressure energy P2 P0, that is atmospheric, same is this, plus half the kinetic energy, half rho will be same, V is taken as V then square, and the potential energy is rho g. Now this reference is matching with the point itself, so there is no height, so rather this height we can take as 0, so this ultimately will become 0. So but else this is not taking part, is cancelled. So rho g h on the left side is equal to half into rho into v square on the other side. Rho also cancelled out, so v is equal to under root of 2 g h. So this is your speed of efflux, or ejection. Okay, so this is comes under Torricelli's law. Okay, so for any reservoir, just like we can assume for our household, from a bigger overhead tank we are getting water through a small tap. So this have the same situation where the cross section of the tank is much more than the tap itself. So whatever velocity will get through the tap, it's only depends on the height of the tap from the surface of the tank. So accordingly we will get velocity. The more the height, we will get more velocity. So we can see that for multi-storage building where we are residing to the lowest or the lower end of the apartment, we will get more pressure in our taps. More pressure we will get because the height is more. Okay, the velocity will be more because that will make more sound, or very fast that water will come once we'll open the tap. Whereas in the same apartment, if you go on the topmost floor, you will get less velocity there. You will not get very much pressure. You will feel on your hand. Okay, so this is because the height is more or less in the two part of the apartment. Okay, so this is comes under Torricelli's, and this is the speed of efflux. Okay, so now we'll learn few more things related to this. What are the things can be learned from this? This is the height of fall. So this also can be related some extent with this motion, and when it will flow, it will after some time definitely will come down and it will move some distance, not nearer to the tank, some away from the tank. So this is the range. So there are two things, range and time of fall. So these are the two things can be related to this. So how can, as we seen earlier, that any this kind of motion can be also resembled with the free flowing body against the gravity. So for free flowing body against the gravity, the equations are that displacement is equal to ut. You know this equation, we have learned in our kinematics, so I need not to explain it. V is equal to u plus gt, and v square is equal to u square plus 2gs. Okay, so you know this. This is the time of fall. This is the distance of fall or fall height. This is the final velocity. This is initial velocity, and g is the gravitation. So now, when a fluid is coming out of this, there is only having horizontal velocity. I am taking it as v instead of v2. This as because there is no velocity, you can assume it is nothing. So this is the velocity. When it will come down through the duct, it will come horizontally. So there is no velocity downward. So here initial velocity downward will be 0, or downward velocity will be 0. So this part, if I use this part will be 0. So now what else? What is S? S is the height. This total height minus this height, because S will be the height, this one. So S is equal to H minus small h is equal to S. What else? Half G is there. T is the time of fall. So from there, what is T? 2 H minus H by G under root. Okay, fine. So now V already have learned from this. What is the speed of influx? V is equal to root over 2G. H we have seen, this height. So with this, if I want to calculate the range, what is the range? Range is equal to the velocity this side into the time up to which it will take to fall height. That much time is having to travel also horizontal distance. It will not get it would not be mismatched, because whatever time it will getting to fall down, at the same time it will travel this path. So both at the time same. So the horizontal velocity in the time, that will be the range. So what is the range? 2gh into under root of 2 h minus h upon g. So now this is cancelled out. 2 it will 2 come out, and remaining is h into h minus h. So this will be the range. Fine. So this will be the, and time of fall also you can calculate. This is the range. So this all you will find. Okay. Now further to that, if I ask to calculate the maximum what are those? The maximum range to derive. So how do you do that? Maximum range to derive. It is not only the formula is needed. You have to derive the maximum range. So the range formula, what I find, is equal to under root of 2 into small h to capital H minus small h. This was the formula. Now let's see what we can do with this. Now this, if I break into, if I remove the bracket, it will be h into h minus h square. So now this equal to 2 into, if I have to put it into formula, so if I take minus common, this will be h square minus 2 into h into small h by 2 to match this part. Up to this is matched. So further, to make it a whole square, I have to bring this part whole square. So I have to deduct the same part out of it. So this will be inside the bracket. Okay. Now let it be like that. Minus h by 2 whole square. I have to do it to balance it, and minus is there. So what I did, this I am matching with this h square minus 2 into h by 2, a square minus 2ab plus b square. I have to put this formula. 2a into b is this much. So b has to bring it in picture. So as it is extra, I have to deduct it. Okay. So now if I allowed to use this part, this is range. Now I take this. So range is equal to 2 into what else? If I remove bracket, the second bracket, this minus plus, so h by 2 will come here, and the remaining, this will be h minus h by 2 whole square will come. So I can arrange it in this way. Now R to be maximum, this part, because this is whole square, that cannot be negative. So this has some value. This is a fixed value because h is fixed. So this has a constant value. So this part range to be maximum, this part has to be maximum, and as because this cannot be negative, this when this part when maximum when h minus h by 2 whole square is maximum, when sorry h by 2 is minimum, then only this whole part will be maximum. If this is minimum, so I will deduct less to get maximum. When it is the minimum one, I will get the maximum of it. So this must be minimum, and as it is whole square, so the minimum value must be equal to 0 only, cannot be negative because the whole square. This must be 0. So what is the value of h? H by 2. So that means if this height is just half of the total reservoir, we will get range maximum. Understood? We will get h maximum. So the condition for R maximum, condition for R max is the height of the tapping has to be half of the tank, and the value of R max is how much? If I put the value here, what is the value? Under root of 2 into h in place h into h minus h, that was the formula. Now put the small h, replace the small h by capital H by 2. Capital H by 2, what will get? The value is equal to 2 into h by 2 into h by 2. So that is equal to 2 into h by 2. So that is equal to 8. So maximum range will be equal to the height of the reservoir, not the height of the reservoir, height of the liquid column initially. So height of the liquid column will decide the range of that. So when height of the liquid column reduce, the range also will come down. So that means slowly this water will come nearer this way, and at some point in time it will be 0 because the height will be 0. When height becomes 0, range also becomes 0. So slowly the liquid will come to the nearer, and at point of time it will fall directly because that will not get any ejection speed. Okay, that will also be correlated. So this is the range. Understood? Okay. In this regard, we will also learn one more thing, that is the but arrangement must be somewhat changed logically. I will tell you why. Now in this context, we will also learn the time to empty a tank or reservoir, you can say. Okay, so now to empty a tank, you can understand easily from your common sense that if the tapping is at height, you cannot evacuate completely because there will be a dead stock always below the tapping. So what you need a hole at the bottom of the tank only. So this is the only changes from the earlier concept, that there we have used a tapping at some height. Okay, where we are measuring the speed of efflux, but that will also be the same case when if it is the hole is at the bottom. But to empty it, this will be the must condition when you need a hole just below the tank, so that every bit of the liquid inside this tank can be emptied. So now if we can assume this is filled with some liquid that has to be emptied from a bottom of the tank. Okay, so this is the case. So now the same, the cross section here is A, this is small a, height is capital H. So what is the condition of evacuating through this hole? we have to empty the complete volume of the liquid inside this through this hole. So volume of liquid equal to in the tank, in the reservoir, in the tank or the reservoir, whatever you say, tank or reservoir, equal to the cross section A into the height, whatever be the shape of the, because if we can assume this is a cylindrical one, the cross section into height. So if we multiply with the cross section the height, we will get the complete volume, and the volume coming out through the hole at bottom is equal to the cross section into its velocity there. At this scale, the velocity in the cross section with the volume it is coming out, and if this is the rate of flow through this, so our time has to be what? The total volume by the rate of evacuation, or rather average rate of evacuation. Why I am saying the average rate of evacuation, I will explain a bit. Now you understand, when height is this one, this velocity through this hole is depends on the height. So the less the height, velocity will be reduced. So through the complete evacuation, the process, that velocity will not be same. Velocity will differ. The speed of efflux will not be same when it is at H, and slowly it is reduced. The velocity of efflux will reduce. So we can say the average velocity of efflux. So what we will take, the average velocity of efflux we have to take, because this is not constant, is equal to the final velocity plus initial velocity by 2. So what is the final velocity here? This will be 0 when it is just about to finish. So you can take 0. Initial velocity depends on this height, it will be 2g and h by 2. So ultimately the velocity that will act, the average velocity is by 2, isn't it? This is the effective velocity, efflux velocity, the average velocity, whatever you say, is this much. So in this velocity rate, this will become A into under root of gh by 2. This will be the effective flow rate. Fine. Now if we use this effective flow rate, what would be our case? Complete volume A into capital H, this H become capital H, okay, divided by small a into gh by 2. So what will be the case? A and A will there, and this 2 will go up, H will cancel that 1H there, and G will be there. So this will be the time, because volume, what is this? The total volume by the volume flow rate will give you the time of to evacuate time, because this is complete volume, this is being evacuated through this is volume flow rate. If I divide the total volume with the volume flow rate, we will get the time to empty. This is the case. So now this is the time to empty the tank. This is the formula. Understand? Fine. So now I will end up, no more theory is there. Right now in this total concept, what we find? What you learned already? We learned. Let me write, and on this we'll do some example or the problem. So what we learned? We learned the speed of efflux, that is equal to under root 2gh. We learned range. The range is equal to what? 2 into h small h, capital H minus h. Range maximum is equal to h for small h is equal to h by 2 condition. And what else? Time of fall you also learned. To what are the formula? 2h minus h into g, I suppose this was the case. The time of fall of the liquid, if it is at some height, small h, range, time, and the third thing, the time to empty is equal to time to empty is equal to small t, capital T will take to distinguish. This is equal to a by a. This was equal to capital A by small a under root of 2h by g. So these are the things we have learned. So on that basis we will solve some problem in next episode. So thank you for now. Keep watching, try to subscribe more and spread awareness to your known group, so that more people will be get advantage out of it. Thank you for now.